Thanks everyone for coming. It's really great to be here. I want to begin by taking a little tour of what we know about exoplanets. The field moves very quickly, so let's make sure we're all on the same page. We'll start with where we were in 1994. My mouse is up here. It's going to hang out up there. Okay. This is pretty much the state of our knowledge in terms of planets around main stars. We had really, really beautiful models of planet formation, though, based off what we knew about the system, the endoplanets. From this, 8 data points were really sufficient to build this complete model. We really felt like we understood planet formation in a really complete sense. Small planets form of 1 AU, there's an ice line, and beyond that, giant planets form, and they stay there for billions of years. And so this worked very well until 1995.
Is that the scale, by the way?
This is it's the typical museum trick of everything's to scale and sizes, but nothing else is to scale. So Jupiter to the sun's about right, Earth to Jupiter, but the distance is wrong. In 1995, radial velocity surveys found their first signals. And so we talk about planets going around their host stars. Of course, that's not quite true. Planets and stars orbit their common center of mass. So star orbits planet, planet orbits star. And so you can see the reflex motion of a star as the planet orbits it. It looks Keplerian, the radial component of the position changing in time. It works extremely well, and the first planet was a half a Jupiter mass planet in a 3-day period around its host star. Hot Jupiter ruined our theories of planet formation. That's okay. We have really, really good theorists in our field, and they're able to develop new ideas. We learned some other things from these first planets, which is that planet occurrence is correlated with metallicity. So more metal-rich stars more often have giant planets. And they're able to reincorporate all of this data and now have new models of how planets form and evolve. So you can see in this plot from 2009, a nice collection of hot Jupiters, a bunch of Neptune-sized planets, a big gap. Remember, there aren't planets between Earth and Neptune, Neptune's about here, and then a lot of rocky Earth-sized planets. 2009 was a particularly fun year for exoplanets because this was the launch of the Kepler satellites. Kepler stared at a field about as big as your hand at arm's length for 4 years, measuring the brightness of 200,000 stars every 30 minutes. Because occasionally these stars have planets, like this. Occasionally these planets are just lined up, so you see their shadow passing across the disk of the star. And so you see this many times in a periodic or quasi-periodic sense. You infer the presence of the planet. The size of the disk tells you the radius of the planet. The spacing tells you the year of that planet. And Kepler worked remarkably well and really changed what we know in many senses. It found thousands of planets. You'll see that the most common ones are between Earth and Neptune in size. What we thought we knew wasn't quite complete as we got the first data once again. We've seen that other things we know are maybe a little more complicated. We knew giant planet occurrence was correlated with metallicity. That's less straightforward. Question?
Yeah, I wondered how many planets were known just before Kepler. It looked like there was a lot of points in that 2009 graph.
So this was not data. This is a simulation.
Ah,
Yes.
right.
And so we knew of on the order of 500 planets. In Kepler now we're on the order of 10,000 planets. And they're fundamentally different planets. These are the radial velocity surveys were sensitive to about Neptune in good cases and larger, where Kepler's planets are predominantly small. Metallicity is less straightforward than that. A paper by John Brewer earlier this year showing that systems of compact multiple planet systems tend to form around low metallicity stars.
Is this theory or observation then?
This is based on data. This is observation.
What?
This is observation. Looking at Kepler data, getting factors of these stars. We can also see that host star mass plays an important role. Low mass stars generally don't have giant planets. FGK stars, sun-like stars, giant planets are much more common. But this is all based on Kepler, which is still a biased sample relative to what we think of when we look out in the night sky and just see planets out there. If we look at on this plot where Mercury is, most of these planets are far interior to Mercury. They're very short period objects, 10 days, year, 10-day year, some of these planets. And if we look at the planets that we really selfishly care about, the Earth-sized, Earth-like planets, we don't really see anything at 1 AU and 1 Earth radius. Not that they're not there, this is just a sensitivity completeness cut down here. That as we move down, these are the planets, smaller signals that happen less often, that are harder to find. So what we really want to do is find these small signals. How do we develop new methods to find the planets that are missing in our data?
Can I ask you a question?
Yeah.
Why are there so few Jupiter-sized planets from Kepler? Is that observational bias?
So the true Jupiters in every sense of Jupiter is an observational bias. Jupiter will transit once every 12 years. It's a 12-year period, you're in one position, you have to wait for it to pass along your line of sight. So it transits once every 12 years. Kepler is a 4-year mission, so it sees 0 or 1 transits of any Jupiter. As you move further away from your star, the probability of passing along this line of sight to transits becomes smaller. And so the odds of seeing a Jupiter relative to an Earth or a Mercury go down very quickly as well.
Well, what about the hot Jupiter?
The hot Jupiters, these are just rare relative to other systems. That it's something on the order of 1% of sun-like stars have a Jupiter. One thing that was found from Kepler was that the hot Jupiters were found a little less than they're found locally for field stars, in a way that's still not fully understood. Maybe it's a multiplicity effect, maybe it's a metallicity effect, maybe the Kepler field is a little metal poor. There's a couple theories that really haven't been fully.
Okay, because before that, I guess the sort of numbers that were thrown around is something like a quarter for hot Jupiter, like a quarter of the all known exoplanets.
That was because the early RV surveys were very biased towards hot Jupiters. Hot Jupiters were all of the first planets we found because they're so easy to find. It's a giant signal, orders of magnitude larger than the Earth signal, and has a 3-day period to wait for it. Hot Jupiters are a small minority of the actual planets. So once we find these stars, or once we find these planets, then we also want to know about stellar activity. How do these stars affect the planets, their atmospheres, potentially their habitability, and how does that change across the age of these systems? So let's dive right in by looking at the Kepler field first. Kepler, I think everyone is familiar with, but you might not be familiar with the details about how the mission works. This is the Kepler field of view. There's about 100 square degrees here. Several 100,000 stars are observed every 30 minutes. In practice, this means that only a small fraction of these pixels are actually downloaded every 30 minutes. The data transfer rate to download the entire detector is too high, and so small postage stamps are selected. It looks like this. This is one star observed by Kepler. This is the second star. And so you can see a PSF. They select a small region to download every 30 minutes, and a small subset of this region that's actually assigned to be this star. And then the Kepler pipeline uses aperture photometry, which sums up these pixels, counts how many electrons are detected, and that's the signal that's given out to the community as the light curve for the star. Aperture photometry works remarkably well in this case. It's fast, and it's found thousands of planets. I don't think we can argue with the success of Kepler. But there's lots of fields where this might fail. Here's an example up here. You can see a cluster. Let's zoom in. This is NGC 6791. It's an old cluster. It's 8 billion years old, and it's metal rich, about twice the metallicity of the sun. This is what it looks like not in Kepler. Kepler's pixels are 4 arcseconds on a side. This is what it looks like in Kepler. And so you can imagine aperture photometry is going to struggle here. How do you decide what pixels go to which star? How do you separate out overlapping stars here? This is a comparison. This is cluster. This is Kepler field. This is Kepler data for some other quasi-random fields. And so it's a much harder problem here. The Kepler team has noticed this is a problem. They ran some of this data through the Kepler pipeline, searching for planets. They found 15 signals, 15 planets near this cluster. There's only one problem. They all had exactly the same period in phase. So maybe you shouldn't believe those, or you've got a really good paper to write. But this is because there's an eclipsing binary that's 70% heat, and it's about a 2-day period just next to this cluster. And so the flux from this bright saturated on the detector EV goes up, dilutes, causes effects on all of these pixels that get picked up by the pipeline. So we want to focus on ways that aren't necessarily just aperture photometry to look in this cluster to try to find planets. And so we can actually model the response of the Kepler detector using PSF modeling, point-square function modeling. And this is helped by Gaia because we know very precisely where all of these stars are in this cluster. And so we can pinpoint their positions precisely and then model the PSFs. The Kepler PSF is a bit of a mess, but the Kepler team characterized it very well before the mission began. And so in the corner of the detector, it looks like this, like a tooth at high resolution. And this is on the actual scale of the Kepler pixels. And so this gives us a really nice place to start. We know that the PSF looks approximately like this, and then can use this to build a PSF and then apply it to every star in a cadence and build a light curve with this. This is computationally very slow, much slower than aperture photometry where you're just counting up pixels. But we can use TensorFlow here, which has not in a machine learning neural net sense, but just through its really fast numerical techniques to speed up this process and make it computationally tractable. And so in this way, we can build light curves for the entire cluster. This is an example of one. So if you're used to Kepler data, this looks familiar to you. There are large jumps every quarter as the telescope rotates, and there's long-term trends due to thermal changes on the telescope over a quarter. These are somewhat enhanced here because over the mission, over each quarter, we assume a constant PSF inside of that quarter, and the PSF is changing slightly, but very slightly on a long-term scale, and so it doesn't affect anything the transit time scales. And in this case, you can see something happening 6 times during the mission. So you can see at my eye, this is a binary, it's very 20% deep, but you can see some of this right there. And so then we can search for planets and find planet candidates towards this cluster. Because we have Gaia, we know the proper motions of all of these stars in the detector in the sky, and so we know that a couple of these are, well, probably good planets, planet candidates. The stars aren't consistent with being in the cluster. There's chance alignments for stars. But the others seem to be consistent with planet candidate signals in the cluster in 791. Along the way, when you look at 6,000 stars, you find new things as well beyond planets. There's some new eclipsing binaries that we find. Here's an example of one. You can see a primary eclipse, and then 2.5 days before it, there's a secondary eclipse. So this is faint star in front of a bright star, faint star behind a bright star. What's interesting about this one is that these are the only 6 eclipses in the Kepler data. It has a period of 200 days, and is 2.5 days between the primary and secondary eclipse. So this implies the eccentricity of the system has to be at least 0.92, which makes it the most eccentric EV that we know of. There's lots of other stellar variability. You can see short period, probably a binary star system, with flare on it. There's a cataclysmic variable that's previously unknown in this field. These are the only 3 outbursts during the Kepler mission. These typically have outbursts of 10 to 20 days, so suggests anomalously low mass transfer rate in the system. And so Julie Skinner, now at Smith College, is helping us understand these. She really understands cataclysmic variables in a way that no one else actually does. So we can say a lot about these planets, what we see. We can also say something about what we don't see. There aren't any hot Jupiters here. And this is, hot Jupiters aren't super common, but it's on the edge of being weird that we would find zero, based off of occurrence rates. However, we know that tidal inspiral can destroy hot Jupiters. We've seen this in the case of LOS 12, where over 10 years you see a short period decay, presumably as the planet is spiraling into its host star. And it turns out that if you have a Q of 10 to the 6 for this cluster, which is at the order of magnitude of what Q should be, then this removes enough hot Jupiters, about 2/3 or 3/4 of them, over 8 billion years, should spiral into their host stars, and then it's fully consistent with us expecting to find zero. Okay.
What's the age of that cluster?
8 billion.
2 billion.
8.
8.
Eight,
Okay.
yes. Yeah, so it's metal rich, and so you'd expect it to form more hot Jupiters, but 8 billion years old, so much older than the sun. Which also means the main sequence turned off, if we're looking at really on the main sequence G K-stars. So Q of 10 to the 6, this is probably reasonable. This is mostly found through theory and then looking at eclipsing binaries. There's no reason that short period binaries have to have the same Q as isolated stars. At the order of magnitude level, Q is probably about 10 to the 6. Can we say something better with tidally inspiraling systems? Well, the answer is maybe. In the near future, tests will look at the Kepler fields. And so with an undergrad student, Chris, we looked at what will tests actually see in the Kepler fields. TESS is much smaller than Kepler. Kepler had an 85 centimeter field of view aperture. TESS is 10 centimeters. So in terms of collecting area, it's only 1 or 2% the collecting area of Kepler. So the planets that we'll find are only the really high signal to noise cases. But it will find the hot Jupiters. These are the high signal to noise transits. And so Kalista then looked at all of these hot Jupiters and made predictions on what the timing precision tests will have on them based on how bright the stars are, and looked at what level of Q would be needed to be able to detect tidal inspiral, which then means if we don't see tidal inspiral, what can we rule out? Most of them, stars at 10, 20, 30-day periods, you shouldn't see anything, so most of these are really no constraints. But some are interesting, because a half dozen or so down here at Q to the 5, Q to the 7, where either we detect tidal inspiral or we can rule out for these couple stars Q smaller than 10 to the 7. So there's some opportunity here in the future with tests. If you're not familiar with tests, it's an all-sky survey in that it observes 80% of the sky, almost all sky, for at least a month. The field of view is 25 degrees by 100 degrees, observes one field for a month, steps, and goes around the sky in that way. This is one example, one image from tests. You can see features you might be familiar with, the LMC, the SMC. There are naked eye stars on there. And then because we're mapping a rectangular grid onto a spherical sky, that doesn't work perfectly, and so you get a field that overlaps every time you step around, and one camera is observed for about a year. So we get long-term, longer period plans than just one sample. Kepler and TESS are a little different in that the TESS pixels are much larger. It's a much bigger field of view. The pixels are about 5 times the size, which means the field looks much more crowded. There's more, same number of stars on fewer pixels. And so if we look at the two on the same pixel scale, there's a difference. The TESS field, in some sense, every field is a crowded field. And so crowded field photometry, like we're using for Kepler, could be powerful for tests to find planets that characterize overlapping stars with PSF's overlap. And so I'm working on that with some friends in the audience here, Dan, Rodrigo, and Megan, as well as with a master's student at the University of Chicago, Adina Feinstein, who normally I would say is applying to grad schools, but instead was just admitted to Columbia. She's great, maybe you'll meet her next year. But building tools to make light curves for everything in the test's images, search them for planets, and have tools to use PSF photometry, especially in crowded fields. It's all on GitHub. Feel free to play with it, submit some pull requests, or find some issues. Yeah, have fun with it. She's made a lot of really great progress in the past couple weeks now that we have real data. And so we found some new planet candidates. Here, these two are consistent with being planets. Here's an eclipsing binary. You see it's 20% deep and then 5% deep alternating. New contact binaries, RLI-rays. And of course, because this is an all-sky survey, you see everything that goes on in the sky. There are some supernovae in the test field of view. Some stellar outbursts, it's not a supernova, but these four are supernovae. And so there's a lot of really fun science that can be done both in stellar astrophysics and beyond stellar astrophysics. Another difference between TESS and Kepler is that the planets orbit really bright stars. And so these are the stars that you can get radial velocity observations for. You get more parameters than just their radius and their period. Maroon X is a spectrograph to be built set to Magellan, to Gemini North in the next month or two, being built at University of Chicago. I'm involved in some of the software for it. But it'll do a lot of test follow-up, especially for low mass stars. Similarly, CCA is involved with the Terra hunting experiment, which will do some test follow-up of other stars in the next few years. Understanding all of these stars and these planet parameters are really important because right now we really have radius and orbital period to do inference with in many cases. Often that's all you need to make really strong inference to understand planetary systems very well. One case where we've seen a lot of success with that in the past few years is looking at the so-called photoevaporation gap. This is a case where I think theory predicted observations really, really nicely. We know all of these short period planets, and many of these shouldn't be massive enough to hold on to their extended atmospheres if they have them. And so planets with atmospheres should have them boiled away. And then bigger planets can retain their atmospheres because they have stronger gravity here. And so if you look at the radius of planets as a function of their orbital period, you might expect to see a population of planets with puffy atmospheres and then a population of stripped cores. This was predicted several years ago by James Owen and Yinchen Wu, and in 2017, this was seen in the data. It wasn't seen originally in Kepler data because there's so much noise on the individual radius measurements, but with either high-resolution spectroscopy to measure host star parameters very well, or astroseismic observations to do the same. That's gray and red points on the slides. You can see exactly the same situation. A population of stars that are consistent with being puffy atmospheres and then stripped cores. We could learn more about these if we had masses for these systems. Right now, we really just know radius and period, and we're inferring that these are these two cases. We don't know anything about their densities. We really want to measure masses. For tests, this would be easy, given that we can get RVs. For Kepler and K2, it's a little harder, but one option is to look at dynamical interactions. If you have two planets in a system that are near resonance, every time they pass each other, they will exchange energy and angular momentum. One is accelerated, the other is accelerated in the opposite direction, causing the transits to arrive earlier or later than you might expect. And if they're near resonance, this happens in a coherent way, causing a sequence of transits that then arrive earlier or later, and we call this transit timing variations, TTVs for And this has been observed by K2. This is observed and used to great success in Kepler as well. K2 observed fields for 80 days at a time. And so we can see here one system, K2 146, where the transits more or less fall linearly until the end. There's something strong happens, and the period changes, and transits all start arriving later than you expect. This was noted at the time. But now that we're near the end of the K2 mission, now we're at the end of the K2 mission, K2 observed various fields in the ecliptic and started running out of ecliptic to observe, and so started observing fields that had been previously observed in earlier campaigns. It's only noticed that 5, 16, and 18 all fall on top of each other, and so we have regions that were observed 3 times now. So once we got data for 16 and 18, the system that I just showed you was at 5. We decided to look and say, do we see TTVs? How strongly do we see them? Can we characterize the system very well? And so I'm working with a first-year PhD student in Chicago, Aaron Haman, who looked at this and found, recovered the signals in campaign 16 and 18. You can see really large TTVs, several hours in amplitude, with just these 3 campaigns of data. And this was there's only one planet known in the system. And so something is perturbing it. We don't know what. And so I said to Aaron, well, why don't you go back and see, we have 3 times as much data, so we're sensitive to root 3 smaller signals now. So maybe this planet's just not transiting, but maybe it is and we just missed it. So go back and see if you can find a planet somewhere in this data. And so he came back the next day and said, I found a second planet in the system, because we didn't see it with 1 campaign. That's wonderful. That makes total sense. How small is it? How much smaller a planet are we able to find? He said, no, it's a pretty big planet. We just couldn't find it in 1 campaign because it wasn't transiting in campaign 5. And I didn't believe that, but he convinced me that actually that's exactly what's happening. There are 2 transiting planets, and if you model the system and then go back and look at where all the transits line up for campaign 5, you just barely see something pretty small, and it's just much deeper in campaign 16 and 18. This is because we have 2 planets that have torqued each other, and so 1 planet was just barely transiting and has fallen further onto the disk of the star, off of the limb, and now it's fully transiting. And the other planet has moved up in impact parameter and is working a higher chord across the star than it was previously. And you can see over 3 years of Kepler, the impact parameter changes by about 0.1 stellar radii. So we have 2 transiting planets here. We have radii for both planets because they are at such strong interactions with each other. We also have their masses extremely well. And so we can look at where they are on this plot from earlier, radius gap. And we see that 1 falls below and 1 falls above the radius gap. We can learn something here. But what's really interesting is they have just about the same mass. They're consistent with having the same density. And this is not a rocky planet density. They have to have either a significant ice layer, and these have 2.5 and 4 day periods, so they probably don't have a whole lot of ice on them, or an extended atmosphere. So this doesn't really make sense from what we think we know about photoevaporation. This one should be evaporated away. But this is plotting radius against period. There's nothing intrinsic to the system about period. And in fact, this looks at this, how long it takes around. But this system orbits an M dwarf, where all of these other ones orbit FGK stars. So if we reframe this in terms of stellar insolation, how much light they receive from their host star, they both move really nicely into the puffy atmosphere again. And so we very often see this in terms of radius and period, because that's what we have, that's what's easy to measure. But it's not telling a complete story. So we really want to understand host star properties very well, and planet properties, to be able to really understand the physics of photoevaporation, what's going on here. We have to get planet masses, we have to understand stars. And stars are challenging because they're very dynamic. If we can look at an example here, This is from a website that Megan Bedell led the effort on, but made with myself and Adina, my students. And it's kind of fun. I put up a link here, so I'm not sure if it'll work. It shows up over here. But if you've not played with test data, it's pretty easy. You just press hit me and you get a random star observed by tests. And so you can see, oh look, here's some sort of variability. Maybe there's a star spots. You hit me again and find things that might look interesting to you. And if you find something that's really interesting, you can just submit it to the archive right away. Okay, so now I have to figure out where slides went. The danger with there we go. Variability, more variability, more variability. The moral of the story is that when you look deeply at stars, all stars are variable stars. The sun is a variable star. It changes photometrically by about 0.1% in brightness, both because of dark spots and bright faculae on its surface, coming and going over an 11-year activity cycle, and also just over a rotation period, as spots are anisotropic from one side of the star to the other. And this is really a challenge in finding planets. Let's look at some radial velocity data that was taken for a couple of years. This group observed a star, found a signal with a period of about 40 days, but correctly said this is probably not a planet, even though it's statistically significant, because the stellar rotation period is right around 40 days. And so this is just spots coming into the view, landing on the blueward moving side of the star, so creating an apparent redshift, and then vice versa, creating an artificial RV signal. A real RV signal, but not one related to a planet. So we lose out on one specific rotation period, in finding planets, the rotation period of the star. But stars don't have one rotation period, they have all sorts of differential rotation. And the sun rotates at 25 days in its equator and 35 days in the pole. That's a pretty big region we're cutting out if we just ignore areas around stellar rotation. And we don't just lose that, we also lose signals that would be roughly equivalent to the stellar activity cycle. This is another set of RV data where there's 3 short period planets, which create a lot of this noise that you see, but also a signal with about a 12-year period. And if you look at a proxy for stellar activity, you see the same period in the same phase. So this group also correctly said this is probably not a planet, this is probably stellar activity. But this means we're ruling out stars or planets with periods of about 10 years. It'd be really hard to find Jupiter if you were looking at our solar system, because its period is very close to the stellar activity cycle. So we don't want to just throw these out a priori. Even if we decide we do, the spots and faculae on the surface of a star affect what you learn about the planets. There's a really nice paper about a year ago from Ben Rackham, a grad student at Arizona, looking at how transmission spectroscopy results, so looking at the spectrum of a planet as it passes in front of its star, its atmosphere blocks various spectral features, or lets through other spectral features, changes as the planet crosses over a star spot or a faculae. I found that it actually significantly changes the observed spectrum. So we really want to understand the surfaces of stars, both to better find planets and to better characterize the planets that we do find. And we're really limited here in what we know about stellar activity cycles, stellar rotation periods. There are about 24 sun-like stars, where sun-like is very generously defined FGK stars, where we've measured both rotation period and a magnetic cycle. There's about 24 stars. They tend to fall across 2 tracks, called an active and an inactive branch. This point is the sun, it happens to fall on neither. So maybe we understand it, maybe we don't. But we have lots and lots of photometric data for missions like Kepler. So how well can we understand stellar activity via photometry? We already said the sun varies by about 0.1% on a 10-year time scale and also on a 1-month time scale. And you can see the behavior here of variability caused by star spots when the star is overall brighter, and less variability from star spots when the star is fainter, because the sun has more of its surface dominated by bright faculae rather than dark spots, which kind of come and go together. So there's more bright faculae making the star brighter when there are more spots, which causes the variability.
Can I ask you a question?
Yeah.
In your previous slide, how are the rotation periods measured in this work? Do you know? I know it's not your work.
Yeah.
From the line broadening?
Yeah, so this is largely, there's some of these are going to be VSAN-I, where they have astrosysmology and believe they understand the stellar inclination well, and others will be regular photometric measurements, where they
See some sort of variation?
yeah, just have some sort of time series photometry and can say that we think there's a radiation period of 10 minutes.
Okay, but that doesn't necessarily mean that's the rotation period of the star.
It doesn't, sure, there are other things it could be. We see from Kepler that we are pretty good at measuring rotation periods in that way. We're not perfect at it, but we're decent. With very regular time sampling. With sparse time sampling, it's harder. Very, really hard. So Kepler can find Earth-sized planets. Earth-sized planets are about 80 parts per million signals in Kepler data. It's about 1/100th the size of the sun, so about 1/10,000th the area as it passes in front of the sun. So 0.1% should be easy. We think of Kepler data as looking like this: a flat line, right at 1, occasionally pockmarked by small transits. That's not what it looks like. This is after a lot of processing. Raw Kepler data looks like this. We see jumps every quarter as the telescope rotates by 90 degrees to keep its solar panels pointed towards the sun, leading to the star falling on a different pixel, which is more or less sensitive, into a big jump here. We see ramps every month after the telescope points back to Earth to downlink its data, points back to the field, takes a couple days to thermally re-equilibrate. Other effects that don't matter for finding transits because it's a very long time scale, but would completely overwhelm any part per thousand level effects over a decade. So it's actually really hard to measure stellar activity cycles just with raw Kepler data. However, there's another observing mode that Kepler used, which is using these full frame images. This is about half of one. You saw one at the front of this talk earlier. Kepler once a month downloaded the entire detector. So there's 52 of these over the Kepler mission. And there's 2 benefits to these. The first is that you have the entire field of use. You have all of the star. You don't just have the small postage stamp around the star, you have this entire PSN. The second benefit is that you have all of the stars. You don't just have the 200,000 hand-selected stars, but you have 4.5 million stars in the Kepler field of view. So lots of other stars that you can use for reference stars to do photometric calibration with. So we don't just have this piece of the PSF, we have everything. And so we built some software that a then undergrad, now PhD student at University of Washington, Guadalupe Tovar and Dan Mackey, built some software that takes a chunk of the Kepler field around a star that you might care about, borrows from our friends in computer vision to identify other potential reference stars, identify an aperture for the star that we care about, a bunch of other stars to do photometry with, and then get absolute photometry once a month across the Kepler mission. And we said we have 20 stars that have decent activity measurements. Well, Kepler observed thousands of sun-like stars, as narrowly defined as you want for sun-like stars. So we look at stars with effective temperatures within about 150 Kelvin of the sun, and search for variability, and we see a lot of it. For about 10% of all the stars we detect, significant variability over the Kepler mission. These are some of the most extreme ones. The sun has a 0.1% variation. Some of these are 2% peak to trough. So there's a lot of variability here. The 4 colors represent the 4 different orientations Kepler during the mission. And so if you saw something on one, you might just expect a bent pixel or something, but here we see things on all 4 channels at the same time. Okay, so we have the long-term behavior of these stars. What can we say with this? Well, we said earlier that the sun has more variability when it's brighter because it's dominated by faculae rather than dark spots. We can do the same thing with all of these stars because they were observed every 30 minutes as well. And so we can see how their spot behavior changes on fairly short timescales. So let's look at one star in particular, and you can see right away. When the star is overall brighter, there's less variability, and vice versa. When it's overall fainter, there's much more variability. And so this star is the opposite of the sun. It's dominated by star spots rather than faculae. So we can repeat this for all of these stars, see which ones have a star spot dominated surface, which ones have a faculae dominated surface. And it turns out it's a pretty strong function of rotation period. The rapid rotators are spot dominated, slow rotators are faculae dominated, with a pretty rapid transition at about 20 to 25 days, so just a little bit younger than the sun. This is something that's kind of been theorized before to happen at around 15 to 25 days, but it's the first time it's been really clearly seen with such a big stellar, solar-like sample. So the dream is to then apply this for stars across the entire Kepler field of view, and understand not just in sun-like stars, but stars across the main sequence and off the main sequence. So that when someone looks at a RV signal like this, they really know what the stellar surface can be doing and how it can be changing as a function of time to understand, is this a planet in your data, or is this stellar activity? So in the last couple minutes, I'm going to look towards the future. And I know that I've heard it said that every time you put an equation on a slide, you lose half the audience. But bear with me here. CCM is close. You can bring it in. I talked about Kepler and long-term variability. TESS will have an opportunity here as well. TESS will give us photometry at a high precision and high cadence for a month. Won't do so well in the long-term stuff, even in an extended mission. But we're going to have photometry on all of these stars, these bright nearby stars, from LSST at a lower cadence every 3 days, at a lower precision than not tens of parts per million, but enough to see millimeg level variations in some cases. We also have Gaia data. Gaia, very rightfully, people think about it as an amazing exercise mission, because it is. But it's also doing really wonderful photometry and providing millimeg level photometry for stars out to 15th magnitude, about once a month for a decade. And so combining TESS and Gaia will be really powerful to understand the longer-term behavior of stellar variability, and this will help us understand stellar activity. TESS is also going to be very useful in concert with ground-based facilities to understand planetary systems. We'll measure radii and periods with TESS, we'll find planet signals, go out and follow them up with ground-based surveys, including the Terra hunting experiment, or NEX, and understand planetary systems. Gaia will also be powerful here because the planet's TESS finds in very short periods. Gaia will look at these same stars and be sensitive to the Jupiter analogs, and the actual, not hot Jupiters, but actual Jupiters, planets in 580 orbits. And so TESS and Gaia together will really help us understand full architectures. Okay, and now the math gets a little crazier, so hang on tight here. We have stellar activity that we're going to understand. We're going to take this knowledge and integrate it across all the planets that we understand to really understand then when we take observations with James Webb, what is going on the surface of the star, how does this help us understand the transition spectra that we observe, what can we really say about the atmosphere of this planet and its composition. So now that half, quarter, and eighth of you are paying attention, I just want to say, great to be here. It's always great to be here. I'll leave my main points up, and I'm happy to take any questions.